Okay, just waiting for people to join us. And I know we had a little technical difficulty there. Sorry I'm not in. My little one was sick, is sick and tired of being sick. He might sneak into the frame to give you his award-winning smile. And I'm just waiting for people to join. Okay. Let me see if they're the same link. That page. Video embed. All right, let me just see if it's working. Da-da-da. This is week 10. All right, CY, I didn't do it. Insert YouTube. Let's get rid of that. I know, I gotta wait till mom comes in, okay? Where am I now? There you go. Oh. Not today. Still waiting for people to join me. Please refresh your web page if you haven't already. Week 10. Week 10.
It's been a shape of the generator. This generator.
Yeah. Okay. No, let's see what's going on. I'm waiting for my kids to join me. Okay, I see someone joining me. That's good. All right. My students.
It's me. Yeah.
You should see a link to start a conversation, maybe. You should see a link again, hopefully, on the screen, maybe. If not, I don't know. I can listen to these headphones if someone has any questions. All right, people are joining. And I am going to begin going over the quiz. If you can see the link to chat me. Oh, I hear somebody. All right, so in any case, I'm getting started, and I'm going to start with the quiz, and let's do that. I'm going to share my screen, and I'm going to go to the quiz. Let's see here. Not that. Let's see here. Let's do the screen. All right, so it's hard for me to know who has what problems, so I'm just going to kind of go over this and see if we're on the same page, and then I'm going to take out your lab, and hopefully it can help you with the lab. I know people had questions last time, so let's go ahead and do this. All right, so the rat probably was a bit challenging, and if it was challenging, it's because we've had some days off. I'll see what they look like. Any case, number one, given the reaction, okay, I have two oxygen atoms coming together. All right, so it's hard for me to know who has what problem, so I'm just going to kind of go over this and see if we're on the same thing. Okay, so we have two atoms coming together to make O2. So clearly you should understand, oops, too big. Clearly you should understand that a bond is being formed. Okay, that's one thing you should do. Bond is being formed. Okay, now the question is energy being absorbed or released? Well, this is something that is in the basics of bonding. Why do atoms bond? If you look at oxygen, it's 2-6. It wants to have two more electrons to have a stable configuration of 2-8. It's not there yet, so it needs two electrons. So we draw an oxygen, each with what? 6 valence electrons. And we learn that each oxygen that we draw has to bring a pair into play here in order to feel like both sides have 8. So my friends, you should see that a bond is being made here. Okay, now the question is what happens? Well, if they're both going to be 2-8 now by sharing, they both have a stable electron configuration, as stable as their noble gas on their same row. Stable means low energy. Atoms that are not bonded have high energy. Think it like this. You've been to those parties where people are single, and when they are single, they tend to want to be noticed. They got those peacock feathers out, and they say, look at me, look at my new hairstyle, look at my new clothes. They dance a little harder. Okay, they want to get noticed. And then once they finally bond and have maybe a significant other, they become the boring couple that sits in the corner. Bonded atoms are that boring couple. They have low energy. So we go from high energy single atoms who do not have electron configurations or filled to filled low energy. So how do we go from high energy to low energy? Energy has to be released all the time. Energy is released to form a bond. Okay? And no one has chatted me anything. Just checking back here. If you have that ability, great. I'm sorry if you haven't figured that out yet. But back to my screen share. All right, share screen again and back to where I was. All right, where was Jarnell, right? Yeah, okay, not there. No, no, no. Where was I? Not there either. Sorry, people. Oh, there we are. Okay. So back to reality here. So number one is a bond is formed as energy is released. If you don't like that, if you want to break stuff, like later on today, let's go out inside and break stuff. Okay. You would need energy to break bonds because bonds that are made are stable. To make them unstable, you need energy. So to break stuff, you need energy. Therefore, to form stuff, energy is released. One is A. Two, who is the greatest ionic character? Now, the greatest ionic character, you have to start to think, what does ionic mean? You have to know these differences. Ionic means what? Sharing. Was it sharing or is it transferring? Ionic means you made ions. So metals like potassium would lose their valence electron and they would become what? Positive, and they would attract other things that become negative because of a transfer. Okay, so the greatest ionic character is the one that has the what? The greatest ability to transfer. Think with me and Kara. Okay, who pulled the rope aggressively away? The non-metal, because the great difference in electronegativity. So I'm looking for a choice that has the greatest ability to transfer electrons. Okay, so two ways you can go about doing this. Number one, recognize who's covalent. Things that are covalent have similar electronegativities. HCl is a what? Non-metal and non-metal. They both have high electronegativities. Water, H2O, it's H and O, both have similar. CO2. So I just took out, my friends in chemistry, the covalent. And covalent, because they have similar strength for electrons, are sharing electrons. And if they're sharing, they're terrible at pulling the rope away. So I've got two of these guys left, LiCl and Kf. How do I know which one is better at being ionic? Well, who has the greatest difference, okay, in electronegativity? I can spell difference in electronegativity. Look at lithium and look at chlorine and look at K and F. Now you could look these up in table S. You can do table S, look at the electronegativity and subtract them and see who has the biggest difference. Or you can look at a periodic table. Now if I look at a periodic table, I can see that I have some stuff written here, so let's get rid of that. Okay, I can see that the greatest difference is going to be in scenarios where I have the what? Smallest element hooked up with the biggest. So I have what? Lithium, and then I have chloride, and then I have potassium, and I believe fluoride, right? I don't know. Did I? What was it? Short-term memory's gone at this height. Here it is. So I've got lithium and chloride, and then potassium and fluoride. Okay, so lithium and chloride or potassium and fluoride. Who is the biggest out of the two metals? Well, you would say potassium. So it has the smallest electronegativity. And who is the smallest element? Fluorine. It has the greatest electronegativity. So K and F, my friends in chemistry, would have the greatest difference in electronegativity. It's the one that's farthest down with the one farthest up. But if you don't like anything like that, go to table S and do what? Subtract these two electronegativities, and these guys would have the greatest difference, which means they have the greatest difference in strength, and they have the greatest difference, or the greatest ability to pull electrons away. So KF has the greatest difference. Again, you can go to table S and subtract your heart away, but knowing the trends is very helpful. So 2 is D. Number 3, why does NAF conduct electricity only in the aqueous or liquid phase? NAF is a metal nonmetal. It's ionic. And as we learn, ionic compounds okay, have ions. And ions conduct electricity only when the ions are what? Free. When are these ions free of the crystal lattice they normally make? When they're in a liquid or aqueous phase. So the best is, because salts, and a fancy word for ionic compound is salts, when melted, that's liquid, or dissolved, aqueous, have free ions. 3 is B. Number 4, what is the Lewis dot diagram for the compound magnesium oxide? I see oxide, I see magnesium, which is a metal. This tells me this is an ionic compound. I have a metal and a non-metal who has two very different electronegativities. The difference in electronegativities is great. So there's going to be a transfer. If there's a transfer, you're going to have ions. Someone's going to gain electrons and someone's going to lose. The metal loses to become positive, okay, and the non-metal gains to become negative. So we're not going to show sharing, okay? This is showing sharing. This is showing sharing. So I'm left with brackets and charges. But I know magnesium from the periodic table likes to lose 2 electrons. Therefore, it's going to be positive, okay? And oxygen has 6 valence electrons. And if you don't like it, start from scratch. Oxygen has 6 valence electrons. Magnesium has what? 2. So what's going to happen? Oxygen, being more electronegative, is going to transfer and take the electrons, like I took the rope away from Kara, and it's going to gain 2 to fill its octet and now become 2-8. It becomes -2. Magnesium comes +2. And that's why E is the answer. Do not confuse, party people. Do not confuse ionic with covalent. This is an ionic one. So therefore, you brackets and charges to show transferring. Okay, number 5. Which compounds has a non-polar bond? Okay, non-polar would mean you are sharing equally. Why would you share electrons equally? You would do so because you have the same strength. Me and my evil twin Mongo have the same exact strength. So the rope between us, when you pull on it, would not be shared more so than the other side. Here's the electron right down the middle. If we have the same attraction for this electron called electronegativity, pinky up, we'd share equally. So the only choice here that has the same element with the same electronegativity is A, N2. Diatomic elements have to have nonpolar bonds because the electrons between them have to be shared because they're both high in strength for electrons. But because they have the same value, same strength, they're shared right down the end, and no one side has more electrons than another. Therefore, there's no differences and there's no poles. Okay, I'm going to stop for a second to see if there's questions on the chat. I'll be right with you. No, I don't see anything. So I'm going to continue on. Probably can't get to it. We'll work those things out. Hopefully, I don't have to do this anymore. All right, moving forward. We just did, no, that's not it. Went over here, Java. Okay, number 6. Which of the following compounds has the most polar bond? The most polar bond is the one that is sharing electrons the most unequally. And the most unequally would be what? Well, if you notice, here's a non-polar bond, so get out of the way. And now I have a bunch of what? Non-metals bonded to non-metals. These are all covalent bonded. All right, so these are all polar bonds, but the most polar bond is where the difference in electronegativity is the greatest. Since these are all hydrogen, if you look in table S, these will be all 2.2. All right, these are all the electronegativity values of hydrogen. So the greatest difference would have to occur with the element that has the greatest electronegativity. And notice these are all halogens. So who has the greatest electronegativity? Well, it'd be fluorine. It's 4.0. If you take 4.0 from table S and minus 2.2, okay, what are you going to get there? Okay, well, you're going to get 1.8. That's a big difference. Okay, therefore, it's sharing electrons the most unequally. And that would have to be. Now, notice something. This is very similar to who's the most ionic in character. You're right. If it is two elements, X and Y, the more that once the electrons are pulled closer than another, they get more polar because you got one side having more electrons, but they also get more ionic in character. It's the same thing. Okay, even though there's no ionic compounds, having ionic character means you're getting closer and closer to when you're actually pulling the electrons away. So the most polar bond is the greatest difference in electronegativity, and it's essentially the same thing as having the greatest ionic character. Even if you don't have ionic character means the ability to transfer. Okay, number 7. What's the shape of CH4? So the answer for number 6 clearly was letter E. What is the shape of a CH4? Well, if you do a Lewis dot diagram, each carbon has a 1 pointing out, and then we have the hydrogen. Okay, I don't know why I have this one right here. Let me get this one out. Now you can see that we have what? 4 polar bonds. 2 different nonmetals have 2 different electronegativities. So I've got 4 polar bonds. But because those polar bonds are all the same in all directions, we would say that the molecule is going to be nonpolar. Okay, that's important that you see, because of symmetry, that the polar bonds are the same all over. It's nonpolar. Now, what's this shape with a 4-sided? A 4-sided molecule, tetra means 4, tetrahedral. Okay, so that's why E is number 7. All right, pH 3. Well, my friends in chemistry, the first thing you realize that we're dealing with P, who has 3 valence electrons, actually 5 valence electrons. But P is a what? P is a nonmetal, and H is a nonmetal. A nonmetal are forced to share because they have both high electronegativities. If they're sharing, we're not going to show brackets and charges. B and D are showing choices that they're ionic. They're sharing because they have similar electronegativities. They both are high. Nonmetals are small atoms. They attract their electrons greatly. So 2 nonmetals are going to fight between these 2 electrons, and they're forced to share because no one has a great enough difference in electronegativity. You've got to get this down. A great difference in electronegativity is ionic. Metal, nonmetal, bigs versus small. It's the same stuff we've been learning the last 3 units. So I'm looking for sharing occurring. Now, the correct sharing. Well, phosphorus has 5 valence electrons. Hydrogen has 1. So we draw this so that each hydrogen brings 1 to the table, and notice by what? You put out the valence electrons, evaluate, and you get 8 for the P. Evaluate for the H by sharing. Each H feels like it has 2, which fills its energy level. So I'm looking for the phosphorus to have the 8. These 2 don't make any sense because they have 8 electrons showing hydrogen. Hydrogen's only going to have 2. That's why choice E is the answer for 8. Number 9, water. Okay, well, water is what? Well, if you don't know anything about chemistry, you've got to learn that water is polar. The meaning of life is water. We're surrounded by it. Okay, so water is 2 lone pairs, and I show it this way because I like to show that the molecule has a bent shape. The 2 lone pairs in center bend it downward. Okay, and you can see that the oxygen by sharing has 8, and by 8 sharing it has 2. Okay, so water is what? Well, you know that it's asymmetrical. Okay, that's important. It's not the same all the way around. Don't get lost by this word. Asymmetrical distribution of charge is a fancy way, pinky up, of saying the electrons are not even all the way around. Most of the electron density is being pulled toward the oxygen. So this side, the more electronegative atom, is going to be the negative side. The side that has the electrons pulled away, the least electronegative elements, will be the positive side. This is a polar molecule. Its charge is distributed asymmetrically. Okay, now the problem is it is asymmetrical, okay, and you would say that it is a polar molecule because of the asymmetry. If you drew water this way and said, well, Mr. Grodsky, what if I drew it this way? Shouldn't it be linear and now be symmetrical? Yeah, but if you think about the shape of water, we've been through this, this is not the flat way. Remember, water has a bend shape because 4 electrons bend themselves in a tetrahedral shape. Here's one H, here's another H, and then we have a pair of electrons coming at us and then a pair of electrons behind us. And you can see that's not going to be a flat shape like that. It's a 3-dimensional shape. All right, so it's polar because it is asymmetrical. It has 2 polar bonds, and these polar bonds create an asymmetrical distribution if the shape is asymmetrical. And these lone pairs bend these bonds downward. Okay, 10 and last one. I'm also taking a lot of time doing this, but I hope this has been helping you to like rethink and re-understand, because tomorrow you're going to get another rat of 10 questions like these again. Number 10, how many pairs of electrons are shared in an N2 molecule? Okay, shared between the N2 molecule. Think with me. Here's an N. It's got 5 valence electrons. Here's another N. Okay, it also has 5 valence electrons. First thing is you make one bond, and then you evaluate. Well, you can clearly see that this N, by sharing one pair right now as a pair, 1, 2, 3, 4, 5, 6, only has 6. So what do, party people? We make another bond. So we put another bond together, and there I go. And now evaluate. Well, by sharing this as 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. Each N has 7. The only thing you can do is put another bond together. So obviously they love to pick on N2. This is a Regents question, okay? And you can see when you evaluate that each N now has 2, 4, 6, 8 apiece. Now it's not sharing 8. In between the 2 nuclei, or in between the 2 nitrogen, is sharing how many pairs? 1, 2, 3 pairs. And you should know that each pair is a bond. Okay, so it's sharing 3 pairs right between the ends. So 10, of course, is D. Now, I could have been nasty and put 4 here so you would think that, but I didn't. All right. Hopefully that works. All right. Please take out your lab. I have a couple of minutes left. Take out your lab, and I want to be able to take some questions. If you need to have a question, I know Kelly had a couple of questions. I want to be able to handle a few of those as well. Take out your lab. Yeah, Brady. All right, bud. Okay, we're taking out your lab. And I guess no one has been able to get on the chat, on the group chat here. Don't know if that's working out. Guess it's not, because I know people would be flying up some crazy things on here. But if anyone can give Kelly any questions you have, and I'll go over them. I know people were having some trouble with the lab a little bit. Hopefully you're picking this up. This is the toughest spot here of the bonding. Polar, nonpolar, ionic, covalent. All right, I'm going to go to one of the last. I'm going to go to like the second page. I think that's probably a place where problems are starting. So I'm going to go to the second page here and share away here. Well, I'm going to stop at the first page. Okay, I'm going to stop at the first page because I want something to recognize something. So let's do that. The first page was by far the easiest, I'm sure. So the Lewis diagram for BrCl, you should have the following. Br, oops, too big. Br had 7 valence electrons. It's a halogen. And Cl had 7, so it's a nice kind of pairing. Okay. And there's the Lewis dot diagram. The ball and stick model for BrCl would look like this. You'd probably have one connected to another. And maybe I would shade this one a different color to show that it's 2 different atoms. Okay. Now, Br is more electronegative, Cl is more electronegative than the Br. So actually I would have no, I won't do that. This would be a polar molecule, but we'll talk about that for a second. We have a bonds. So this is a polar bond. Why? Well, because there's 2 different. Why is it a polar bond? I got your question. I'll take that in a second. Polar bond because there's 2 different nonmetals. 2 different nonmetals sharing unequally. They have different electronegativity. This pair of electrons being shared supposedly closer to the more electronegative atom. Now the question is the molecule polar? And the molecule is definitely a polar molecule. Now why? Only has 1 bond, so there's no other bond for it to cancel, but by the way, it's asymmetrical. So it's a polar molecule. There's nothing to offset the other one. Okay. And of course, the shape is linear. So I'm going to take a couple of questions here. Someone just asked, what is the major characteristics of polar and nonpolar? Now, when you talk about polar and nonpolar, you have to think, am I talking bonds or am I talking molecule? If I'm talking bond, the major characteristic is that you have 2 different nonmetals, like HCl. When you look at HCl, okay, these guys are 2 different nonmetals. That means they have 2 different what? Electronegativities. And the one that's more electronegative, and you can look that up on table S or know your trends of the periodic table, that's going to pull the electrons closer on this side and make this side more negative. And the side that does it is more positive. That's the bond. This is a polar bond. So the one way to identify is that you have 2 different nonmetals will always give you a polar bond. So anytime you look at the ones above, like N2 that we just did, okay, that is a nonpolar bond. Why? Because there's 2 of the same element sharing equally. So here they're sharing equally down the middle, here they're sharing unequally. So an easy way to remember in terms of the bond is same nonmetals have to share equally nonpolar. 2 different nonmetals, always polar. Okay? Now bonds, you have to consider the shape. Since HCl only has 1 bond, it's creating an area rich in electrons on one side and an area poor in electrons, which is the H side. So HCl and BrCl are both polar molecules because they have an unequal distribution of electrons because of the polar bond, okay? And they're both asymmetrical. And yes, the scratch off had a problem. That's okay, we'll fix that. Okay, and I like having problems in the scratch off because it makes you think. Now, KCl, you should have realized, guys, that K is a metal. Cl is a nonmetal. You should have realized you should have showed a transfer of electrons. You should not have shown sharing. I threw some ionic ones in here to make you think about this. So these are all these other questions are non-applicable. So if you run into something ionic, it's non-applicable. None of these questions mean anything if it's an ionic compound. Metal and non-metal. Okay? So I'm going to throw something. You have to differentiate between covalent sharing, sometimes what? Unequally, sometimes equally. And then you have to realize that in ionic, there is no sharing. Someone pulled the rope away. And what gives that away is the metal. Okay? Now, if we go to the second page, and I know I'm running out of time. Okay? We've done some of these already. All right? So in any case, time is up for me. All right? Homework is to continue working on the second page if you haven't done so and labeling bonds, type of molecule. Tomorrow, I'm going to give you, tomorrow I'm going to give you another rat, so I might post something online today as some more practice. Okay? So check out tonight's homework. It'll be a way to again, practice if you're having problems. Thanks.